Welcome, guys and girls, to my first sequel of some videos I dubbed Hardware City, because in this videos I just want to talk about hardware topics and hardware hacking. This is a very interesting counterpart for me, instead of always dealing with software topics, because I'm originally coming from the hardware world, and this is something that's more familiar to me than always talking about software. Okay, and the first sequel I will talk to you about in RF transmitter, the Aurel TX-SAW433, this one. This tiny little device, manufactured by the company Aurel in Italy, is used for mainly for remote switching and domestic applications, like those domestic RF switches, when you can switch on or switch off power plugs to switch lamps and electrical devices in your house, something like that. And it's very simple and reliable circuit, and there's a counterpart existing named the Aurel RCRX. It's also a tiny little device, which is the respective receiver, also working in the 433 frequency range, which is dedicated to ISM purposes, as you may already know. Okay, I already used this little chip for some domestic applications, as I already told you, but I want to do more with it. And as I wanted to do more with it, I discovered a flaw of this little device. And I think this flaw is related to the bunch of harmonized standards written here in the datasheet this device must fulfill to be released in the European area. To go deeper in this problem, I'm going to show you how this device generally works. If you take a look at this datasheet, which is very poor, it lacks a lot of information, but at least you can see here the symbol of this device, and you can see it has two modulation inputs. And when you apply voltage to this modulation inputs, you have one input for low voltage, namely 5 volts, and then you have an input for a higher voltage, namely 12 volts. Then the transmitter starts to work. But it only exhibits one small impulse. Even when you keep the modulation voltage high, the transmitter is switching back to idle mode after a short time. So you have to work with impulses. You have to apply impulses to the modulation input, and these impulses are transmitted from this transmitter to the receiver side. If you want to work with this device in a continuous mode, that means that you can switch on this transmitter and it stays on as long as you apply the modulation voltage, then this won't work. And I thought about this problem because I want to use this transmitter also for transmitting data, or maybe for using it for CW applications, when you want to, for example, implement some kind of simple Morse transmitter. And so I decided I had to find out where the problem lies with this thing here. And I took my magnifier glasses and watched very carefully the circuit here, if I could, let's say, re-engineer a schematic of what's implemented here, and so get a deeper understanding of where the problem is. And I'll show you the schematic. So here's my schematic. You see it's written by hand, so maybe it's not very clearly, and somehow a little bit ugly, but anyway, it would be enough to explain the contents of the circuit. What I found out is that you have an input for the supply voltage, which is VCC here. the apply voltage is decoupled against the RF energy with a decoupling capacitor. This is a very straightforward and normal approach when you're doing RF designs. Then we have a choke here, some kind of power choke, which is working as a, let's say, working resistor for the amplifier. And here you have a series of capacitors and an additional inductor. And also one capacitor more that is connected to the antenna. So this is part of a matching network for getting the generated RF voltage to the antenna. Here I recognize is a footprint of an unplaced electronic component, so I think maybe this was considered as some kind of low-pass filter or extended matching network, but it isn't used obviously. Okay, here we have the amplifier, the heart of the oscillator. And you can see this is a standard NPN bipolar transistor in base configuration. That means the base of the transistor is grounded in terms of AC. And it's grounded not for a very big area of frequencies. It's grounded only for a small area of frequencies, and this is done by use of this crystal here. The crystal is connected to the base of the transistor with a capacitor to keep it away from DC, because crystals don't like DC voltage. And that means if you know how a crystal works, you know that one configuration of a crystal is that it works as a series resonance circuit. That means it becomes low Z at its specified frequency, and when it becomes low Z, then the base of the transistor is connected to ground in terms of AC. When it's connected to ground, you have a classical base configuration where the input of the amplifier becomes, where the emitter of the transistor becomes the input of the amplifier, and the collector becomes the output. And the output energy here generated at the collector is routed back to the input by use of this feedback capacitor, which is very small. So a small amount of the output energy is routed back to the input. The input is classically low Z, therefore the capacitor must be very small in order not to load the output, which is high Z. And all the rest here, those resistors here, are for biasing the transistor. You know, every transistor needs a bias. That means it needs a constant collector current flowing through the transistor, and the collector current specifies the amount of amplification the transistor is possible to realize. And you have a resistor here of 15 kilo ohms from the base to the ground, and you have two more resistors going to the respective modulation inputs. This is a modulation input mod 1 for applying a small voltage of 5 volts running through a 3.9 kilo ohm resistor and then going into the base. And this is the second modulation input, where you can apply 12 volts running through a 21 kilo ohm resistor going through the base. So this is a very, very straightforward approach, because when you read a book about hardware, you know that the base configuration with a transistor base connected to ground is provides a high amplification, also very high frequency that can be generated. The emitter is routed through a 100 ohm resistor against ground, because the collector current is generating a voltage here which is needed for the bias of the transistor. And the 100 ohm is AC decoupled with this small capacitor against ground, so that no AC voltage can apply here, because it would be decreasing the amplification of this circuit. So that seems to be a very, very easy approach for a transmitter. The question remains why this transistor and this amplification circuit oscillator doesn't work continuously. And the reason lies in these two little components here. You see a resistor and a capacitor. And this in fact is a very tricky little circuit that forces the oscillator to work only for a very small amount of time and then switches it off automatically. And to understand this, you have to think how this circuit works when you switch on the modulation. So let's say you have a power supply here and at the start moment no modulation voltage here. So now you apply a voltage. So what happens? The voltage generates a bias at the base of the transistor. So a current starts to flow from VCC through this power choke, through the transistor, out on the emitter, and through this resistor against ground. So DC voltage is generated here. This capacitor is charged immediately because it is connected directly to the voltage. But this capacitor here, in the moment of applying the modulation is empty. When this capacitor is empty, that means that virtually this point here is connected against ground. Because the resistor configuration here specifies how much collector current flows, that means that in the moment of switching on the modulation, the 67 ohm resistor is in parallel with a 100 ohm. And when it's parallel with the 100 ohm, that means that the effective resistor is only 40 ohms. When it's only that means that the collector current is almost doubled. When the collector current is doubled, that means that the amplification of the circuit is also doubled. And when it's doubled, the oscillator starts oscillating. When it starts oscillating, it generates RF energy, but this capacitor is charging up during this process because the voltage here slowly charges up this capacitor through this 67 ohm resistor, and as more it charges up, the lower the current becomes here, because the current is specified between the difference of the voltage at this point and this point. So the collector current goes down more and more and more, up to the point where the oscillation rips off because the amplification is not big enough to keep it going. And that's a little trick how the designers of the circuit ensure that the transmitter is only switched on for a very short moment. And I think that it does so is a requirement from the standards the transmitter has to fulfill. So you can see this is my little test setup I made. This is the transmitter soldered on a piece of standard PCB. This is my breadboard. I supply this circuit with 5 volts. And this is the modulation input, and this is my monitoring receiver scanner. I already dialed the right frequency. Now I will put the modulation input to 5 volts and listen what happens. You hear the small crack? Again, again, again. This is a small impulse generated by the transmitter. This is switched on and immediately switched off again. Okay, now the question is, what can we do to get rid of this annoying behavior? And the answer is simple. We just have to bridge this capacitor. When you bridge this capacitor, then this point is always connected to ground. Then this resistor is always lying in parallel with this one. We have always the 40 ohms, and we have a higher collector current always running through the transistor, always providing enough amplification to kick up and keep it running, this oscillator. And this I'm going to show you now. Okay, now I bridge the capacitor here, as I showed you in the last picture. Here's my scanner, I switch it on. Okay, and I applied a small push button here that routes constant voltage of 5 volt to the modulation input of the transmitter. And now watch here the RF level indicator when I press the button. Oh, that was RF remote control switch from my neighbor, I think. Okay, now I push a button. And you can see we're at full level, and the level stays high as long as I push the button. Now I release the button. Level goes away. Again I push, and it's at full power again. So it works. Thank you guys for watching.